Hello viewers. In this chapter, we are going to discuss the dynamics of circular motion using various examples. When an object moves in a circular path, its velocity changes continuously, resulting in acceleration towards the center of the circular path. This center-seeking acceleration is termed as centripetal acceleration. Its magnitude is v square by r or omega square r. If the object is of mass m, then the magnitude of the force acting on the object is going to be mv square by r or m omega square r. To define centripetal force, we can say it is the force required to move an object with a constant speed in a circle. Now, if we consider our frame of reference is on the object moving with uniform speed along the circle, then a balancing force is required to explain the equilibrium of the object. This force is termed as centrifugal force. It can be considered as a reaction force to centripetal force. The magnitude of centrifugal force is exactly the same as of centripetal force, and it is always directed opposite to centripetal force. We apply concepts of centripetal force in explaining various observations happening around us. The first example we are going to discuss is vehicle motion on a circular road. When a car goes around a circular track, a centripetal force must act on the car to keep it on the circular track. On a level circular road, this force is provided by static friction. Equating the centripetal force and static friction, we can get an expression for the maximum velocity with which the car can travel without slipping. We often see the banking of the roads at curves. For safe drive at the curves, the outer edge of the curved road is raised above the level of the inner edge of the road. This is termed as banking of road. Generally, the frictional force is not adequate to provide the necessary centripetal force to a speedy vehicle. Banking of road helps in providing necessary centripetal force for the speedy vehicles. In this example, we will consider no frictional force acting between the vehicle and the road. Here, the horizontal component of the normal reaction is providing the necessary centripetal force for the circular path. Using simple mathematical steps, we can find an equation relating the angle of banking and the maximum speed with which a car can travel safely without slipping on a banked curved road. In the next example, we consider frictional force is also acting between the vehicle and the road. Equating the components of the force in horizontal and perpendicular directions, again we can obtain a relation for maximum speed with which a car can travel without slipping on a banked curved road. Here, if we put 0 as the value of coefficient of static friction, that is, if we consider no frictional force, then we will get the same equation which we have obtained in our previous example. The next example is related to the bending of a cyclist going around a curved path. Let us consider the cyclist is inclining at an angle theta from the vertical axis. Here, the horizontal component of reaction is going to provide the necessary centripetal force to the cyclist. Equating these two forces and with certain substitutions, we can obtain an expression relating the bending angle and the velocity at which the cyclist can take turns safely without slipping. At next, we are going to discuss the motion of an object in a vertical circle. In this problem, generally we need to find tension on the string at various points and velocity with which the object must move so that the object moves in a circular path. From the figure, the components of various forces at different positions can be observed. We can obtain the expressions relating tension on the string and velocity at various points. At the lowest point, tension on the string is maximum, and at the highest point, tension on the string is minimum. Now let us obtain the minimum velocity at h with which the object must travel so that the path of the motion remains circular. In this case, tension on the string should be 0 at the top. Putting the value of tension, we can evaluate the velocity at the highest point. Next, we have to obtain the minimum velocity at L with which the object must travel so that the path of the motion remains circular. In solving the problem, we have to take the help of energy conservation law. Using this law and with simple mathematical steps, we can calculate the minimum velocity at the lowest point with which the object must travel so that the path of the motion remains circular. We have to remember these are the limiting conditions. If an object moves with more velocity, then the path will also remain circular, but in that case, the tension on the string will increase. Similarly, we can obtain the expressions of velocities when the string is at horizontal position. We can also find the difference in tension in the string at the lowest and highest points. We can also generalize the above problem, and by carefully resolving the components of forces, we can obtain an expression relating tension on the string and velocity of the object at any arbitrary position. If we put specific values of theta, we can obtain the expression which we have obtained earlier. To summarize, in this chapter we have discussed dynamics of circular motion using various examples such as motion of a vehicle in a curved path, banking of roads, inclination of cyclists at curves, and vertical circular motion under gravity.